Yeah. 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 Yeah.
All right, so I hope everyone's doing well. Last time we kind of worked our way through a couple of theorems, and so it was kind of a little bit of technical work, but we were using it to set up for today. So let me just remind you of what the first uniqueness theorem was, because that's the one we're going to take advantage of today. What it said is that the solution to Laplace's equation at del squared v is equal to 0 in some volume is uniquely determined if v, first of all, I mean, of course, it has to satisfy Laplace's equation. And then second, it has to match the boundary conditions of the surrounding surface S that encloses whatever volume we're interested in. So if you can find that v, no matter how you do it, you're guaranteed that that is the correct solution and it's the only solution. So we're going to really try to take advantage of that fact. What our goal is to come up with a couple of methods for finding potentials that will satisfy Laplace's equation and match the boundary conditions. If we can show those two conditions are satisfied, we know we have a solution. Okay, and so the first technique that we're going to use to find these potentials is called the method of images. And so it's 3.2 in the textbook. And the way we're going to do this is we're going to do it through an example. So let's consider a point charge Q at distance, let's say Z equals D. So we'll put our point charge on our Z axis. It's going to be a distance D above the XY plane. But in that XY plane, we're going to put a conducting sheet. So above a conducting sheet at Z equals 0. And moreover, the conducting sheet is going to be held at V equals 0. Another way of saying the same thing is that that conducting sheet is grounded. And what grounded means is just that it's like, in a practical sense, you take a wire and you connect it to whatever you want to ground, and the opposite end of the wire is connected to a big metal stake that's driven into the ground. And the way to think of conducting planes are that they can acquire a little bit of charge, or they can give off a little bit of charge without changing their potential. So they sit at potential 0 always. It's like a reservoir of water, right? If you take a little bit of water out of the ocean, the volume or the height of the water doesn't change. So you can add a bit of water, you can remove a bit of water from the ocean without changing its overall properties. Okay, so anyways, the question is, what is V of X, Y, Z in the region Z greater than 0? So above this conducting plane. So let me draw the picture. So we'll have a coordinate system. We'll call this our Z-axis, and then we have our Y-axis over here, and here is X. And we put a plane inside this, well, it sits in the XY plane, in fact, it sits like this. Something like this. I can't draw an infinite plane, so I'm drawing a piece of it. These arrows mean that they extend out and fill the whole XY plane. And then we have our point charge Q sits over here, and that's a distance D up the Z-axis. Okay, so fair enough. Maybe we could just emphasize that the potential is 0 here in this blue plane. So I mean, that's a hard problem in general, like using the methods that we have so far. So we want to come up with a kind of a new approach to this problem. And so what we're going to do is, instead of trying to solve this like immediately, what we'll do is we'll just sketch the electric fields and the potential, what we think it might look like, and maybe, who knows, that might lead to some insights that will help us solve the problem in general. So before trying to solve this problem, let's sketch what we think E and V will look like in the region Z greater than 0. Okay. All right. So I can't draw in 3D very well, so I'm gonna take a side view of this thing. So we're gonna look from this edge. So maybe we're looking along the z-axis, let's say. Okay, so I'll start my side view over here. All right, so let's see. I'll have my z-axis sit here, and here's my y-axis, like so. My plane that sits at my plane at v equals 0 sits right here. And so we're looking at the edge of this thin plane. So this is our conducting plane with v equals 0. Okay, and where's my point charge? My point charge sits over here somewhere. So let's say this is Q. We'll just say it's positive, just so we have something to draw. All right. Well, what do we know? Let's start with the electric field. Close to the point charge, the plane won't be affecting the shape of the field that much. So for positions close to the point charge, what we expect to get is just this radial electric field that's pointing out something like this. All right. And then what we could do is we could say, well, look, if we are in the region above the point charge, then again, I don't think the plane is going to really affect the shape of the fields that much. And so this sort of just continues on with the radial field, something like this. Maybe I could put a few more in, something like that. Maybe we start to get a bit of distortion as we start getting closer to that plane. But, you know, so far, maybe something, actually, I'm gonna fix my distortion, something a little bit like this. All right. And then what else do we know? Well, how do electric fields intersect conducting surfaces? They're perpendicular, yeah. So whenever these electric fields get to our conducting plane, they have to hit it perpendicularly. Now, would you expect the electric field to be stronger near the center of this plane or off to the sides? It's near the center, okay? So that means that these electric field lines have to spread out as we move further away from the z-axis. All right. I mean, it's going to look something like that. What we just have to do is we have to connect these lines up. So our electric field lines are going to look something like this. I'm going to draw a couple more here. Okay, so that's roughly what we think our electric fields would look like. Okay, so E, it's going to be something like that. All right. If I wanted to draw the potential, how is the potential related to the electric field in terms of like drawing? Yeah, I guess, so what is the direction of a line of constant potential relative to electric fields? Perpendicular, that's right. So near the point charge, if I want to be perpendicular to my electric field, I end up drawing these little circles. So we initially get these kind of concentric circles around here. Do the circles, if I want to have the same change in potential from one line of potential to the other, do the actual potentials get closer together or farther apart as the electric field gets weaker? Farther apart, right? So strong electric fields, the potential is changing quickly, so your equipotential lines are close together. So that means they're close together near the point charge where the electric field's strong. And then as we move out, they're going to start spreading out. And all I'm going to do is I'm going to try to maintain a perpendicular line intersecting these electric fields. And, you know, maybe my drawing's not perfect, but you end up starting to get these distortions away from circles, especially when the region that is between the plane and the point charge. Okay, and so these dashed lines are equipotentials. All right. And we sit here and we look at this and we say, oh my God, that looks like a complicated shape. How are we going to solve this problem? Does this look familiar at all? Can anyone recognize, like, have you ever seen that kind of pattern before, or at least part of it? Yeah, I'm not looking for a shape. I'm looking for a configuration of charges that gives something that looks a bit like that. Not everything exactly the same, but similar. Yeah.
Charge equal like a distance negative t on the other side.
Yeah, is that what you're gonna say? Yeah, that's right. So that's an electric dipole, right? So this looks like half of the electric field and potential that results from an electric dipole. Let's draw the electric dipole. So for a dipole, what we'd do is we put some Q here greater than 0, and we put some Q here less than 0. Let me call this the position halfway between. This is Z equals 0, and we'll call this a distance Z equals D, and this is a distance Z equals minus D. All right. And so I want to draw the electric fields that we would get. I'll just say, instead of saying a negative Q less than 0, I'm going to say it's exactly the negative of the red charge. Okay. Well, for a dipole, electric fields are going to point from the positive to the negative, and they're going to do this kind of thing. And so, sorry, I'm going to draw over top of my dimensions here. So that's okay. And we'll add one more. And then away from the positive charge, we're going to get this sort of behavior. And then electric fields point in towards the negative charge. Anyways, it's something like that. And if you compare these two pictures, you know, maybe they're not exactly the same, we don't know yet, but the top half of the dipole looks a lot like the fields that are above the grounded plane in the top picture. Okay, so what does the uniqueness theorem tell us? It tells us that if we can find a potential that satisfies the Laplace's equation and the boundary conditions, then it has to be the right solution to this top problem. I don't care about what's going on for Z less than 0. I was asked only to find the fields for Z greater than 0. So that's the region I care about here. So what are the boundary conditions? So in our original problem with the infinite plane, our boundary conditions would be the boundary condition. We're going to start using the term boundary conditions quite a bit. So I'm going to do B dot C for boundary conditions. just let me, I often use B/C for because, so we need to distinguish between B dot C dot and B/C. So boundary conditions, what are they? Well, let's go look at this. What would the potential be for Z really huge, far, far away from the point charge Q? 0. Okay, that's one of them. So one of our boundary conditions is in general far away from Q, V has to be 0. All right. Well, another boundary condition is we've got this plane where we're forcing the potential to be 0. So where does that plane sit? That plane sits at Z equals 0. So for any Z equals 0, any combination of X, Y, and Z equals 0, V has to be 0. So let's just say everywhere where, well, that's weird, everywhere where Z equals 0, we must have V 0. Okay. Well, if we now look at our dipole, and let's see, if I was at Z goes to infinity for the dipole, what's the potential going to be? 0. If I was at Z equals 0, the potential is going to be 0 again, right? Close to the positive charge, we're going to have high potential V. Close to the negative charge, I don't really care about what happens in this Z less than 0 region, but just to make the point, we have low potential near the negative charge, and then midway between them, so midway between plus Q and minus Q, V equals 0 at Z equals 0. So we definitely satisfy all of the boundary conditions of the original problem using this dipole configuration, and we're guaranteed that this is going to satisfy Laplace's equation because we know the potential of a point charge, and by definition that has to satisfy Laplace's equation. So therefore the dipole configuration satisfies the boundary conditions. And so since V of point charges must satisfy Laplace's equation, the two configurations above, that is the infinite plane and only one point charge, and then the dipole, the two configurations above must have exactly the same V of X, Y, Z in the region Z greater than 0. This is a consequence of the first uniqueness theorem. Okay. Now, the reason it's called the method of images is because if we look at this, what we've done is, in order to make an equivalent configuration of charge, we've treated the conducting plane as if it was a mirror, and we get an image of this charge on the other side of the plane, but we have to change the sign from positive to negative, or if this was negative, we change this one to positive. Okay. And it is always going to be true that if I have some blob of charge above an infinite plane, then the method of images would be take that exact same blob of charge, put it on the other side, and change the sign, and you'll get the same potential in this region above. Okay, there are other ways to use method of images that don't involve conducting planes, and Griffiths talks about one of them. But then you have to be clever enough to come up with that new configuration that's going to match the boundary conditions and allow you to solve the problem. This is the standard one. So notice that we essentially treated the grounded plane as a mirror, while also changing the sign of the image charge. The next assignment, whenever it comes out, it's not, I haven't even started right yet. But you know, what we might do is instead of a point charge, maybe we have a line of charge above the grounded plane, and so you can use the method of images to solve for that region. Okay, so let's write down the actual solution. So let's see. If we had, let me draw the geometry again so we can figure it out. So here is our XY plane, and here is Z. Here is, say, our point charge Q, and then maybe we are interested in what is the potential at some point P. As long as P sits above the XY plane, we should be able to write down an answer for that. Well, okay, we know that for a point charge, let's see, V is 1/4πε0, and then it's just Q over this script R. So our only job is to find this script R. And the script R, remember, is R minus R prime, where R locates the point of interest. So here it is, and maybe it projects down into the XY plane like this. Anyways, this R is just equal to X hat plus Y hat plus Z hat. Okay, and then we have R prime is from the origin to our source charge. And so in this case, our source charge is right on the Z axis. And so it's just Z. Actually, we said we were going to place it at distance D above the XY plane. So we'll write it as D times Z hat. All right. Well, that means that the script R that we need is just, well, let's see, it's X hat plus Y hat. That's the R. And then we have Z minus D Z hat when we take the difference of R and R prime. All right, well, that means the magnitude of R is going to be X squared plus Y squared plus Z minus D squared. This is for the positive charge. Okay, let's say then that all of this was for the positive point charge. By exact analogy, for the negative point charge, right? So remember, we're trying to solve the problem of the infinite sheet with one point charge above it, but we said that that's equivalent to 2 point charges placed symmetrically about this XY plane. And so that one's easy to solve. So we're going to solve that one, and then say in the end, the solutions must be the same for the two cases. So this is going to be minus Q divided by script R minus. But script R minus we would do the exact same analysis and we would find that this would be Z plus D squared. Because the negative charge is at a position Z equals minus. Okay, so then the total potential in the Z greater than 0 region of our original problem is given by, well, it's just the superposition of the potentials due to the 2 point charges, the negative one and the positive one. And so there's going to be a 1 over 4 pi epsilon naught. In fact, there'll be a q for both of them. And then for the positive one, we get 1 over the square root of x squared plus y squared plus z minus d squared. And then we have to subtract the other one because it was a negative q. And it's 1 over the square root of x squared plus y squared plus z plus d squared. Let me check. Hopefully that's the right answer. Yeah, it is. Okay, so this is the potential which is valid for z greater than 0. And that is the essence of the methods of images. Finding a configuration of charge that's easier to work with and has the same, fulfills the same boundary conditions. Okay, well, let's do a little bit more with this. If we had a ground plane below this point charge Q at Z equals D, you could imagine, like, charges in the conducting plane can move around. And so you have this positive charge sitting above the conducting plane. It's going to attract some negative charge nearby. So let's see how much negative charge is accumulated in that ground plane, sort of just below that positive charge. So now that V is known, it can be used to find the surface charge. And surface charge induced on the ground plane. You know, we could do other stuff too. Just before we start this calculation, I could just take the gradient of this. I could take the z derivative of this thing, and that would give me the z component of the electric field, minus the z derivative. And then I take minus the y derivative, that gives me the y component, minus the x derivative gives me the x component. Add them up, now I know the vector electric field in this region, z greater than 0. Okay, so you already told me that just above a conductor, E is perpendicular to surface. Maybe I should write this as E is perpendicular to the surface. And you might remember that E perpendicular, in this case, is the Z component of the electric field, is equal to sigma over epsilon naught. Do you remember we did this problem where we had a, we used Gauss's law, and we had this charged infinite plane. We used Gauss's law to find the electric field, and it was just proportional to sigma. We're taking advantage of that result right now. Okay, but the Z component of the electric field is minus D. Well, I don't need a partial derivative if it's, okay, maybe I do. The potential, if we take the Z derivative of the potential, that gives us the electric field, the Z component, with that minus sign. is equal to sigma over epsilon naught. And so therefore sigma is equal to minus epsilon naught dv dz. Okay, that will tell us the surface charge density on our conducting plane. We can do this calculation because we already know what the potential looks like. So we're going to have to do derivatives like the z derivative of stuff like x squared plus y squared plus z plus or minus d squared, and this is all to the minus 1/2. Okay, so let's see, if we do that derivative, we're going to get a minus 1/2 factor, and we're going to have to lower the exponent by 1. So the minus 1/2 becomes a minus 3/2. So this is now going to be 3/2. And then I have to take the z derivative of the stuff inside, and we have a term there, z plus or minus d squared. So I take its derivative, we're going to get z plus or minus d with a factor of 2 out front. Okay, and so canceling the 2's, that's our answer for the z derivative. So we just have to put that back in to find our surface charge density. So therefore sigma is minus epsilon naught, but the minus sign from the epsilon naught and the minus sign here are going to end up canceling. So what else did we have? We had a q over 4 pi epsilon naught out front. Q over 4 pi epsilon naught. And then we had the plus, we had the term with the minus sign here. So first we have the one with the minus sign. So it's z minus d, right here, I'll show you, right? The first one is the one with the minus sign, and then we go minus the one with the plus sign. So let's do that. X squared plus y squared plus z minus d squared to the 3/2. There's going to be a bit of writing, but it's actually going to clean up a bit. Then we go minus, and then we have to take the one with the plus sign. X squared plus y squared plus z plus d squared to 3/2. Okay, so I think that's sort of what we got there. Well, what's going to happen? We're going to get a z, and we're going to get minus z. Okay. And so this is going to be, what else can we do? We can get rid of the epsilon naught. Now we're going to have a minus sign in front of both terms, so we can pull that out. We're going to get a d plus d. No, not yet. We'll factor the d out. So we'll factor out minus d. So it's minus qd over 4 pi. And then it's 1 over x squared plus y squared plus z minus d squared to 3/2. My plus, I pulled out the minus sign. So 1 over x squared plus y squared plus z plus d squared, and all of that to 3/2. Okay, so it's a bit of a mess right now. Yeah.
How do you cancel the if you don't have a common denominator?
Oh, yeah. Okay, you are correct. Thank you. Yeah. That is right. They are going to go away, but you're absolutely right. I can't do that cancellation. Thank you. So, okay, then I can't pull out this d either. Because I still have my z. So z minus d, and then in fact, let's not pull out the minus sign, and let's put this as minus z minus d here. Okay, so thank you. I think this should be correct now. The reason the z's are going to go away is because we are trying to find the charge density on the conducting plane. Where does our conducting plane sit? Yeah, so our conducting plane sits at z equals 0. So that means our charge density is going to be, well, now I can do minus q over 4. Well, let's not get ahead of ourselves. When I get ahead of myself, I make mistakes. So we have minus d over x squared plus y squared. And now we're going to have z equals 0. And so we have minus d squared, which is just d squared. And then we have minus d x squared plus y squared. Z equals 0. So this is d squared. And now both of these things are to the 3/2 power. Okay, that's better. Now it is a common denominator. And in fact, I'm going to end up with a minus 2d. So we have minus 2q times d over 4 pi x squared plus y squared plus d squared to the 3/2. Okay, so the 2 is can cancel with the 4 pi, so we have minus qd over 2 pi times that stuff. All right, let's look at our xy plane. So this is the xy plane only. And so our charge surface is sitting in here, right? I think we used it blue. And so it's going out to plus minus infinity in both directions. And what we expect to see is like an accumulation of charge kind of in this sort of region. And I guess it would be negative charge. And look, we have a negative sign, so that's good news. Okay, so if I was to go sit out at a point over here, this would be x and this would be y. So this is x squared plus y squared, and here's theta. So what I'm going to do is we're going to switch to polar coordinates here, and we're going to integrate the charge per unit area over the surface of this plane. And that will tell us the total charge that's induced in the plane. So we're going to switch to polar coordinates. What that means is that x squared plus y squared is going to be equal to r squared. And r, if we have an infinite sheet, it's going to span 0 to infinity. And we're going to have a theta, which will go from 0 to 2 pi. Maybe I should use phi. So let's use phi. All right, phi. Okay, fair enough. And so the other thing we'll do is we'll integrate. So let's integrate sigma over the area of the plane to find the total induced charge. What do you think the answer is going to be? Yeah, let's see what happens. So the calculation we're going to do is Q induced is equal to sigma dA, and we're going to integrate over our plane. Okay, so Q induced is equal to, what were all these constants? Minus QD over 2 pi. So it's minus QD over 2 pi. And then we're going to have the integral of phi is 0 to 2 pi. And the integral of r is 0 to infinity. And we had 1 over x squared plus y squared, we're going to write as r squared. And then we had a plus d squared, and that's all to the 3/2 power.
Two subscripts say?
IND, induced. Yeah. Yeah, so it's how much charge is being concentrated near the center of our conducting plane. And then in polar coordinates, we have to do r dr d phi is our little element, our little patch of area. Okay, so the first thing we can do is we can do the phi integral. In fact, I'm going to put the d phi over here, and this is just going to be 2 pi. It's going to cancel the 2 pi that's sitting there. That's good news. Okay. And then, well, let's see. I'm not good at integrating in my head, so I always have to do these substitutions. U is r squared plus d squared, so du is 2r dr. When u equals 0, when r is equal to 0, we get u is equal to d squared. When r goes to infinity, u goes to infinity. Okay, so q induced is equal to minus qd. We got rid of the 2 pi. The integral of u equals d squared to infinity of u to the minus 3/2, and then r dr equals du over 2. So we'll pick up a 2 here. And we'll do 2. All right, let's see what happens. So we have to raise the exponent and then divide by it. So minus 3/2 becomes minus 1/2. So we have to multiply by minus 2. So we get plus qd. U to the 1 over u to the 1/2 from d squared to infinity. Now look at that, qd. All right, at infinity, 1 over root u is 0, minus 1 over the square root of d squared is 1 over d. And so we end up with q induced is equal to minus q. All right, so that's cute little results. And so that's the whole game with this method of images type problem, is we're going to try and find a simpler configuration of charge that gives us the same pattern of fields and potential. And if we can write down the potential for that simpler configuration of charge that satisfies the boundary conditions and Laplace's equation, it has to be the right solution. You need to be a little creative and a little clever if you want to use the method of images to do like more complicated arrangements of charge, but that's possible.
What would be an example?
An example would be Griffiths. The next example Griffiths does is he has, I believe, not a grounded plane, but like a uniform, like a conducting sphere next to a point charge, and then he comes up with a new configuration. Okay, so I think the homework that we will do, the next homework we'll probably do, it will be a grounded plane type problem, but instead of point charges, maybe we'll have a line charge or something like that. All right, so 3.3. Answer me this. Have you guys and girls ever used separation of variables in another course? You have. Good. Where did you see it?
For EDE's class.
Okay, in a math context. Okay, I'm gonna do the physicist version of separation of variables. In quantum? Yeah, so at 304, is that where you saw separation of variables? Yeah. Did you solve the hydrogen atoms in quantum? You will. So hydrogen atoms is a separation of variables problem. Okay, so it's very good that you're going to see this in multiple courses all at once. So your math course, quantum, and here. So let's see how this goes. So we're going to start in Cartesian coordinates. We'll start with the easiest case first. So what we're going to do is we're going to attempt to solve the partial differential equation. Well, Laplace's equation is the one we want to solve. You know, in general, it would be something like this. Directly, assuming we can write the potential in the form of, like, all of the x dependence would sit in this function capital X, all of the y dependence would sit in this function y, and then all of the z dependence sits in the function capital Z, and then we construct the potential just by multiplying those together. Now, on the face of it, this looks like, you know, almost an absurd kind of conjecture, like what makes you think we could actually do this? Well, I don't know right now. All we're doing is we're sitting here looking at a very difficult problem. And what we're going to try to do is make some guesses, some assumptions. We're going to stick it in there and we're going to see what happens. Maybe we're not going to solve the problem, but maybe we'll get some insights along the way. Okay. So let's see how this works. And we're going to do it through an example, just like we did the method of images. So let's start with a 2D example. All right. So it'll be a 2D problem, but I have to draw a 3D picture. So this is going to be our x-axis. This is going to be our y-axis. And so right-handed coordinate system. So Z would be over here. Okay. What we're going to do is we're going to put a plane that sits. Actually, it'll go over here as well. That fills this space here. And then we'll take a second plane. It's going to intersect the y-axis at this point. And then let's see. Oh, yeah. Let me redo this. I want to give myself a little more space here. 2D example. Okay. All right, good. So now I'm going to draw a blue plane. There's going to be two parallel planes here, and they're going to sit. So we do intersect this axis here, but then we go behind it as well. All right. So we're going to have this blue plane. That's a conductor held at V equals 0. And we have a green plane is another conductor held at V equals 0. These planes fill the space x greater than 0. So they're like semi-infinite planes. They don't go into the negative x region. So we have two parallel semi-infinite conducting sheets, both at V equals 0. One sheet is in the xy plane. The other is at y equals a. Okay, so this point here is a height a above the xy plane. There's one more thing that we need to add to this problem. And that is along this z-axis, both in the positive and negative direction, we're going to have a third sheet. It's going to be infinite in that it goes all the way to plus infinity along z and minus infinity along negative z, but it will be limited to live between y equals 0 and a. So I can try to draw that for you. There is going to be a third sheet that's going to sit right here between the two. And let me just try to give the indication that this keeps extending past and fills in this whole entire space. Okay, and so this extends out this way as well. All right, now there's one thing we have to know about this purple strip. This purple strip is electrically insulated from these two sheets so that we can keep its potential different than v equals 0. I have to have it different than v equals 0 because if I said this was 0, then I have 0 potential everywhere, and the solution is just the potential 0. There's no charge anywhere. So we're going to put some charge on this purple strip that raises its potential to some value, but that charge cannot leak off onto the infinite planes, the semi-infinite planes. Okay, so there is a strip along the z direction. That is at a potential v of y is equal to v naught at, well, yeah, let's say v is equal to v naught, and it can maybe change with y. And so the strip,
You notice you said X, Y plane in the.
oh yeah, you're right. You are right, thank you. So this is XZ plane. You're right. And so the strip is along the Z direction. That part was right. So the strip, sorry, what was I going to say? Extends from y equals 0 to y equals 8. Let me just draw a side view in case that picture above is not as clear as it could be. So here's our y-axis. Here is our x-axis. And what did that bottom one is green. So here's one plane, and this sits at v equals 0. Here's the other plane. This sits at v equals 0. This is at a height y equals a. Over here, we have y equals 0. And then we've got our purple strip here at a potential v naught of y. And there's some kind of insulation between these pieces, so charge can't flow between them. That's the geometry. Okay. Let's see. From this kind of picture, we expect that the potential will change along x, because as we move further away from this charged strip, the potential will change. In fact, we would expect that at x equals infinity, the potential would be 0. We would expect the potential to change along the y direction, because here we need potentially 0. Here it's got to be 0, but in between it's probably not 0. But along the z direction, would we expect any change in the potential? No, the geometry is exactly the same for any value of z. So by symmetry, we expect v to be independent of z. And so that means our general three-dimensional potential we could express as a 2D potential. And if we're going to use separation of variables, we would just write it in this way. All right. Let us write down our boundary conditions. Boundary conditions. There's going to be a few of them. One. Well, whenever y is equal to 0, we're on the green plane and the potential has to be 0. Okay. Another one is, well, if we're at y equals a, we're on the blue plane and the potential has to be 0. Okay. We already, sorry, this will be free. We already talked about the fact that if I go to x is plus infinity, then I'm infinitely far away from the charged purple strip, and I would expect the potential to vanish. And then finally, the fourth boundary condition is that v is equal to v naught of y when we're on the strip, and we're on the strip when x is equal to 0. So those are the boundary conditions that we have to satisfy. If we can come up with a potential that satisfies all of 1, 2, 3, 4, and is a solution to Laplace's equation, we're done. We're guaranteed that that's correct, no matter how we get the solution. Okay, goal. We won't finish it today, but we'll start. Try to see if we can find v of x equal to x times y that satisfies both Laplace's equation and all boundary conditions. Okay, so all we're going to do is we're going to take this potential and we'll shove it into Laplace's equation. Okay, so del squared v is going to be equal to 2x derivatives of the separation of variables form of the potential, and then 2y derivatives, same thing. The beauty of separation of variables when it works is that these derivatives, the x derivative acts only on the x function, and the y derivative acts only on the y function. All right, so this I could write as y, and then it's not even partial derivatives anymore, right? X depends only on the position little x. And likewise, big function y depends only on the coordinate little y. So it's no longer a partial differential equation. We've got some ordinary derivatives. And so that still has to be 0. What's the next step? If you've seen separation of variables already, what would you do next? Divide. Yeah, that's right. I don't like having my y's and my x's mixed up. So I want to separate them. So let's divide by x times y. Okay. So what are we going to get? 1 over x times 2 derivatives of x plus 1 over y times 2 derivatives of y is equal to 0. All right, so this is one of our fundamental starting points. You know, so far we haven't used the geometry of our problem at all. This would just generally be true for any solution to a two-dimensional Laplace's equation using separation of variables. All of the physics of our geometry is going to come from imposing boundary conditions. Okay. All right. You've done separation of variables. What's the next step? Yeah, that's right. You know, I could imagine a situation where I sit at some position x, y, and these two terms have some values. They have to add up to 0. And then maybe I keep my x fixed, and I move to some new y position, right over here. Well, if I keep x fixed, all of the x dependencies here, this number has not changed. But y may have changed if I change my y coordinate, but evidently it didn't, because if these added up to 0 at some point xy, then I move to some new y, this didn't change, so that can't change because it still has to sum to 0. So it must be the case that both 1 over x times 2 derivatives of x and 1 over y times 2 derivatives of y are equal to constants. Actually, the requirement is stronger than that. If this is equal to constant c, what's this one equal to? Negative c, right? That's the only way they're going to add up to 0. So, in fact, the constants are equal and opposite. Okay, so therefore we could say 1 over x d2x dx2 is equal to c, and 1 over y d2y dy2 is equal to minus c. Okay, so this is in order to satisfy, I guess, what did I call it? Star? Yeah. All right. So what I'm going to do next is I'm going to choose to write my constant in a particular way. And it may seem arbitrary, but it's just, I know what the solution is going to be. So I'm going to pick a constant that is going to make it easy to write down the final solution. So for convenience, I'm going to choose to write the constant as c equals k squared. In fact, it's not really hard to see why I'm making that choice. I'm making that choice because we're going to try to solve for big X and big Y. They're going to involve either exponentials or trig functions, okay? And I'm going to have to take 2 derivatives of those things. If I have a derivative of e to the kx, and I take if I have a function e to the kx, and I take 2 derivatives, I'm going to get k down twice, and it's going to be a k squared. That's why we're choosing the constant to be k squared. It's an anticipation of that derivative acting twice, giving that constant back 2 times. All right, so what we've got then is 1 over x d2x dx2 is equal to k squared, or d2x dx2 is equal to k squared x. We'll call that equation 1. And then the y case is, is similar, but not exactly the same. It's equal to minus k squared. And so d2y dy2 is minus k squared y. That's equation 2. So the advantage of separation of variables is that we started with a partial differential equation with second order, hard to solve in general. And now we've ended up with 2 ordinary differential equations that aren't mixing up the x's and the y's. Okay, so separation of variables has allowed us to write our second order partial differential equation as a pair of ordinary differential equations. There's still no guarantee that after doing all of this, we're actually going to get a solution to our problem, but we're still trying, okay? We're still trying. We're going to have to see if we can match those boundary conditions. That's the key. All right, solutions. What's the solution to the first one?
Lambda y, or the first one?
Yeah, I want to do the first one. So simple harmonic motion is the one with the negative sign. Yeah, it's because a mass on a spring is a restoring force. So if you displace it positive, the force is to the negative. So the sine and the cosine is going to be number 2. What's that first one?
The exponential.
It's the exponential one, right? Solution. So to number 1, we're going to get x is going to be the most general solution is like this. Okay, it's probably not even worth doing, but let's do it anyways. Let's take the first derivative. We're going to get down a k from the first term. We'll get a minus k from the second term. And then when we take a second derivative, we get a k down again. And then we get a minus k down again, so we get k squared with a plus sign. And so this is equal to k squared times x. All right, so that's good. So it is indeed a solution to that differential equation. And you can see why I chose k squared as the constant. 2 derivatives brings out the rest. Okay, so that's good. Now for the second equation, you've already told me that it's going to be trig functions. This one will depend on y instead of x. So, sorry, it's not sine times sine. Sine and sine, it's sine and cos. Okay, let's, just for the sake of completeness, we'll take 2 derivatives and just verify that it works. The derivative of the sine becomes a cos. So cos ky. The derivative of the cos becomes a minus sine, so we're going to get minus kd sine ky. And then when we take the second derivative, we get another k out. We'll pick up a minus sign because the cos is going to become minus sine. And then the sine becomes a cos. We get another factor of k, cos ky. And that is indeed k squared times y. So that worked. Just while we're at it, there's probably a way that is there a nicer way to, instead of doing trig functions, what if I didn't want to do trig functions? Yeah, complex exponentials, right? So I could have written this as, and in fact, it probably would have been nicer because I don't like thinking about, oh, when do I have to get the sign involved? But I could have written this as c e to the jkx plus d e to the minus jkx, ky and not kx. Okay, but anyways, we'll stick with what we got. Okay, so therefore, our separation of variables solution is just x times y. And we said x is going to be a e to the kx plus b e to the minus kx, and y is c sine ky plus d cos ky. All right. So far, we've only done a generic math problem, okay? This works for any separation of variable solution to Laplace's equation. We have not used any properties of our geometry at all, okay? So now we're going to actually do the physics. So if this solution is going to be valid, it must match all 4 boundary conditions. Okay, so this is where the physics, now we're doing physics. Okay, 1. What was our first boundary condition? V equals 0 when y equals 0. Okay. V equals 0. Actually, I don't want to start with that one. I want to start with the x one, just because that's in my notes first. I'm going to start with the one that, did I pass them? Here they are. I'm going to start actually with the, which one do I want to start with? Start with v equals 0 when, okay, I'm going to start with number 3. Start with the x one here. Let's start with 3. I want v equal to 0 when x goes to infinity. All right. So there's our potential right at the top. All I'm going to do is put in infinity for x. And so we get a e to the k times infinity plus b e to the minus k times infinity times c sine ky plus d cos ky. And I need that to be 0. All right. Well, what's e to the minus infinity? 0. What's e to the plus infinity? Infinite. So what's the only way that we're going to satisfy this boundary condition? A is right. Otherwise, the thing blows up, and that's not going to match a boundary condition. So therefore, we can only satisfy boundary condition, what was it, 3? If A is 0. Okay, fine. That's okay. Then v of xy in general. So let's see. A is going to be 0. So we're going to end up with b k e to the minus kx times the trig function stuff. But b times c is just some other constant, and b times d is some other constant. So I can absorb b, absorb the constant b into c and d. All right. So if I did that, we would get e to the minus kx times, I don't know, like a c prime times sine ky plus a d prime cos ky. All right. Let me just do a couple more here. We'll do some easy ones. So boundary condition 1 was, well, let's look at it. I think it's probably v equals 0 when y equals 0. Okay, that's good. V equals 0 when y equals 0. Okay, so v of x when y is 0 is e to the minus kx c prime. What's sine of 0? That's 0. What's cos of 0? 1. And we need this to be 0. What does that mean? Nope. D is 0, right? D require D prime 0. Okay, so then V of X, Y. This is kind of nice. We're getting rid of constants left and right. Good. E to the minus kx sine of ky. Let me do one more and then we'll finish. Boundary condition 2. It was V equals 0 when y is equal to a. So V when y equals a is c prime e to the minus kx sine of ka equals 0. How am I going to get 0 here? What's the restriction?
Or K has to be n.
Yeah, n pi, but not n equals 0. Why isn't it n equals 0? If I put in a sine of 0 here, then my potential is going to be 0 for any value of x and y for n equals 0. So we're not going to use n equals 0, but that means k is equal to n pi over a. And now our general expression for this potential is e to the, let me write it as c prime, e to the minus, instead of k, we have n pi x, and then we divide by a, times sine, instead of k, we have n pi y divided by a. We still have to do boundary condition 4, and that one's going to be a little more challenging. That's going to be a sticky one. So we'll pick that up on Wednesday. All right. Thanks very much. We'll see you, some of you tomorrow, others we'll see next week. Yeah. Here, let me see if I can. So this K here?
Yeah.
Oh, it's because you wrote sine K of A, it should be sine K of Y.
Oh, sorry. What? Yeah, I'm putting K into the top one there. This is the special case where Y is equal to A. But in general, we have a sine of KY, and K has to satisfy that condition. I think it's okay. Yeah. 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 Like the very, very top.
I'm having a hard time understanding how the electric field lines that were like above the parallel, how they're sort of.
These ones?
Yeah.
Oh, like some of these will eventually come back to, like, if I was to bring this one all the way over here, like it might hit the plane over here somewhere. It's just that out here, the electric fields can be very weak. And in fact, out at the very edges of the plane, out at infinity, will be 0. So what we have is strong electric field in the center, and it gets weaker and weaker and weaker. These ones above the charge, most of them will just go off to infinity, like a regular point charge. This one might have like a wee little curvature, and maybe out here somewhere it's like, I don't know exactly what it looks like, but it's something like that. Yeah. Yeah. Thank you. Yeah. All right. See ya.